Good morning. Happy 8:30 in the morning here. Thanks for coming. Happy to be talking to you today about KinectforWindows. We're going to do a programming deep dive. I'm very excited to be part of Build 2012 and glad you're all here. Today we're going to be talking about the scenarios for KinectforWindows. You've heard of NUI. We'll talk about some other scenarios. We'll do a lot of coding. I'm going to start from a basic sample and work my way up, walking through a number of important parts of our API. Throughout that time, I'll be talking about the different data streams that come from the Kinect sensor. So there's sensor data streams, and then there's streams that there's data that we recognize from those streams, these recognition streams. We'll talk about those as well. And very happy to have Chris White here as well. My name is Rob Relyea, which I forgot to say. Chris White is here as well, and he'll give a little peek to the future as well, which should be exciting. So, of course, people are familiar with touch-free interaction with the screen. And if you saw Jay Kapoor's talk yesterday, he talked about a lot of the improvements we're going to make in that space. I've got a pointer to that talk a little bit later, near the end of the presentation. Kinect is also taking off in lots of areas that don't involve people. Scanning rooms, being on a robot, scanning objects. Kinect also, with your software, does a good job of monitoring people, making sure they're bending over properly as they lift a heavy box, other training or physical rehab operations as well. And there's a number of scenarios that can combine those three things above. You can build augmented reality solutions that combine both the environment and user monitoring as well. We like to think of those things as three different, those three scenarios as NUI, building a natural user interface. The non-person scenarios, you can think of natural environment observation, so observing your environment. And NUO, observing users. So those are some of the scenarios that we've seen developers and companies get very excited about with KinectforWindows. I'm going to show you a few obligatory architecture boxes and then jump into coding. So we support C++ and managed applications. We now support Visual Studio 2012 or 2010 with our latest update last month, October of 2012, we released version 1.6. When you build a C++ application, you go ahead and depend on KinectforWindows runtime and drivers. Your application should actually chain install the KinectforWindows runtime, which will also install the speech runtime for your speech capabilities. And we run on Windows 7, Windows Embedded Standard, and Windows 8, now with last month's release. For managed applications, we have a managed assembly, Microsoft.Connect.dll, which is built on top of our native runtime. Of course, there's the speech runtime, Microsoft.Speech.dll version 11. And that's built on top of the .NET Framework 4.0 or now 4.5. So a year ago, we didn't speak at Build about Kinect. We were busy still working on our first version. Since last year, we've shipped 3 versions of our runtime, drivers, SDK, and toolkit. We're on a rapid pace, and we're happy to keep innovating and listening to you and reacting to your feedback. So I'm not going to spend a lot of time talking about what came in what version. I'm just going to walk through things, and let's jump into some code. First of all, how many of you have used KinectforWindows SDK? Okay, we've got about half of this crowd. I'm going to start here on my Windows 8 box. I'll press the Start key. I'll type in Toolkit. And this is how I usually launch the Developer Toolkit. When you install the runtime, the SDK, and the Developer Toolkit, we have something called the Developer Toolkit browser. And this Developer Toolkit browser allows you to navigate through a bunch of samples in C#, VB, C++. I'm sorry? My desktop became extended accidentally. So the way I launched this, they'll fix that in editing, right? I go ahead and type in toolkit. The developer toolkit comes up, and I'm able to see C#, C++, samples, components, docs, SDKs that are related, et cetera. If I want to go ahead and run any of these things, or the vast majority of these things, I can scroll down to whatever I want to run and just go ahead and run this. So I'll run skeleton basics. Here I'm tracking my skeleton. And I can go dig into that code. The basic series tell you how to go ahead and deal with skeletons, color, depth, data, et cetera. So that's a great place to start. And that's actually what we're going to do now. So if I wanted to go ahead and install a sample and run with it, I would just say install, choose a place for it to go, yes, open it up, and I would dive in, open it up, and bring it up into VS. Now, what I'm going to start with actually is something very similar to face tracking basics WPF with the face tracking ripped out. And so let's go ahead and open up that project that I added a few things to make the demo go better throughout. So first, let's see this running. Press F5. There we go. We have basically a video feed here. My sample is called Magic Mirror because we're going to go make more magic things happen than just seeing a video feed of me. I'll walk through that code quickly so you understand what we have here. I've got a bunch of variables declared up here. I'm using something called a sensor chooser I'll talk about later. This is a bunch of things involving the color format and storage for color data. This is involving depth data. In my initialization, I want to make sure that my application works well whether there's no sensor in there or whether there is a sensor. Let me do a quick demo of that. Initially, there'll be a sensor. Everything's working fine. If I go ahead and unplug, it'll realize, hey, you need a Kinect. Go plug it in. You go plug it back in. And the app's able to go ahead and get that right on the fly. So Kinect Sensor Chooser and Kinect Sensor Chooser UI are two things that ship in the toolkit that you'll be able to use in your applications to have a more polished application. So in order to go ahead and do that, I wire for the Kinect Changed event. I wire up the UI element to the Sensor Chooser itself, and I tell the Sensor Chooser to start. It's just that easy. And then in the Sensor Chooser on Kinect Changed event, I get told about sensors that go away and sensors that come in there. In the sensors that go away, I unwire things and disable things and stop things. In the sensors that start or that come in, I go ahead and enable things. So I turn on the color stream and choose the color format I'd like. I turn on the depth stream and choose the resolution I'd like there as well. And I can go change skeleton stream, et cetera. We'll go through that. There's two ways to get data from Kinect APIs. Generally, there's a polling API where I can go ahead and say, is there a color frame? Is there a color frame? Is there a color frame now? Or I can register for events. So there's a color frame ready, depth frame ready, skeleton frame ready. Here I'm showing off all frames ready, which is showing basically because we have a couple different cameras and we capture at different times, we want synchronized versions of those color and depth frames and skeleton frames. So all frames ready will provide a synchronized version of all of those frames for me. Let's go down into that handler and take a look at what we're doing here with just the color frame so far. So inside of all frames ready, we use a using pattern, so we dispose this frame that we like of this frame. The system is moving quickly. We need to be efficient with it. We go ahead and set a color image frame to open color image frame off of the event args. If we didn't get one, that means things are bad. I'm behind. I need to catch up, so you're not given one. Here I have some tracking to figure out if I've changed image formats, so I can change my allocations for different bit sizes of images, et cetera. So quickly here, this is just so I can dynamically switch between things. I've got the color height, the width, the format, the bytes per pixel, et cetera. This is my allocation of a byte array for basically 4 bytes for every pixel by default. And then I wire it into a writable bitmap in WPF, and I wire that into an image element in my WPF application. So those things happen just at the beginning or whenever I change format. Then every single frame, I'm going to go ahead and copy that pixel data to my storage that I just created, this color pixels, this byte array. And then again, I'm also going to go ahead and render here, updating my writable bitmap with those pixels, slamming color pixels right into there, and that's how we get the updating. So let's go ahead and just quickly review what we did at each step. We installed the SDK, the developable toolkit. We ran the toolkit browser, and ran a sample, installed the sample, and started modifying it. We saw Kinect sensor chooser and sensor chooser UI. We learned about the all frames ready event, and we started playing around with the color image frame and some of the rendering there. The next step I'm going to do is I want to go ahead and start taking advantage of some of the depth data. So how am I going to do the depth data? First of all, I've already enabled, up earlier we saw that this already enabled, we have already enabled the depth stream. We've turned it on to depth range near because it works better up close for where I am right now. So down here in the all frames ready, I'm just going to copy that code and do something similar for depth, but change a few of the names. So instead of a color image frame, I'm going to get a depth image frame. Instead of open color image frame, I'm going to go open depth image frame. Let me put this on the clipboard. We check to make sure we have a depth image frame. We are checking to make sure the depth image format didn't change. And if we have a new format, we're going to go ahead and keep track of the depth image format. There we go. So we don't need to keep track of all the sizes here because our application isn't changing any of those things. We are going to go ahead and allocate a place to put the depth data. Now the depth data is stored in an array of depth image pixels, which has things, which basically has a depth in millimeters for every pixel, and also has what player, what person is there, player 0 through 6. It basically has a body mask for you. So there I've got the allocation. I don't need to render it at all. I'm going to, every frame, I'm going to go ahead and copy the pixel data to this .depth pixels. And there's 2 APIs to do this. We're going to use the depth image pixel data to. I'll talk about the other one later. So there we have the data, and we don't need to render it at all. So there we go. So that's basically how we go ahead and get the data, make sure it's allocated, and copy it every frame. So now that I have the depth data, I'm going to scroll up to my initialization to my constructor. And I have an element called ConnectImage, which is a custom element that has an image in it with a canvas overlayer on top of it that knows how to layer things on top. I'm going to go ask that. I'm going to register for an event called marker request, which basically is when I go ahead and click on that thing, it's going to go pop up to my app and say, hey, I'd like to put a marker here. I want to go ahead and make it so when I click, it shows me what depth is there. Go down to the bottom, paste that function in, and I'll start dealing with it. So the first thing I need to do is understand what the click point was. And in the event args, I pass along mouse event args. I'll call get position, and I'll ask it for the image element that's within the Kinect image because that's being scaled right now and stretched, and so that's just a good thing to do. I'm going to figure out what color pixel index I have. So I'll take my Y click point and multiply by the current color width and add to that the X click point, making sure to cast to an integer so I don't get crazy results. So this is basically telling me where I clicked, what pixel I would refer to in the color pixel. Now, the problem here is we've got a couple cameras on this Kinect. We've got the color camera and the depth camera. They're very close together, but just because I ask for 100, 100 color pixel doesn't mean I'm going to ask for the same depth pixel to go look up the depth. So I need to do a translation, and that's part of the point of this, this whole code here. So we have a new object in the latest version called Coordinate Mapper that knows about color spaces, depth spaces, and skeletal spaces, and is able to translate between those different things. The way you get this is you go look at the Kinect sensor object, which I have in the sensor variable here, and you just grab the coordinate mapper. So I've got a coordinate mapper now, and I want to map from my color data that I have into the depth data. So I've captured color data, I've captured depth data, and I want a translation between the two, basically a lookup table. And in order to do that, I need to pass in a few things. First, let me get IntelliSense going again, because I don't remember what I'm supposed to pass into it that much. All right, so this dot current color image format. You need to get the depth image format, the depth pixels, and depth points. Depth points is going to be the result out of this. So we need to go allocate depth points. I already declared depth points beforehand. Basically, these are depth image points that are this translation function for us. Over where we allocate for new color frames, we're going to allocate for new depth points because we're going to want to change it at the same time. So every time we get a new color image format, we're going to allocate a new depth image point array, and it needs to be the same number of pixels as the color frame, so I'm going to multiply color height and color width. There we go. So now what we have is we have color data, we have depth data, and we have a translation between them, an array that I can look these things up in. I'm going to bounds check the color pixel index that I just, I'm going to bounds check the color pixel index to make sure that it actually is greater than 0, and I'm not mapping, because they don't map to exactly. If I click on the outside edges of the color photo, it won't map to a place in the depth. So I'm going to go ahead and just make sure it's greater than 0, and also make sure the color pixel index is less than the color current width times the height. And as long as it's OK, I'm going to go look up the depth point. I'm going to look up the answer and look up the color pixel index. And then I'm going to talk to my little Kinect image that knows how to put a pin up there. I'm going to call a routine called getValueMarker, and I'll pass in a few things. I pass in just a unique name, which I get from this event. I pass in the x and the y, click point x, click point y. And I pass in depth point.depth with 0 decimal places. Let's go. OK, so now I can click, and I see numbers. And these are the depths at these different places. If I mouse around and move, it just shows me, and then I can let go. For those of you who can't see this, these say like 2955, 1622, and this is showing me the depth value. Now let's flip over to what we just learned here. Then I'll go make those dynamic and change as things happen. So what we just saw is we were able to show depth at a color point. We learned a little bit about frames and allocations. And we knew that we were able to use Coordinate Mapper to be able to change between the color spaces and the depth spaces. One of the important things to understand, and I'll show you this in a moment, is that depth is greater than 4 meters. In earlier versions, we clamped at 4 meters, and you're able to go ahead and see to 10 meters and beyond with a little more noise. Yes?
Those depth values, are those actually physical? Can be mapped to a physical measurement?
Yeah, the depth values are millimeters. The depth values there were millimeters. Yes? Let's hold that for the questions afterwards. Yes, I'll point out if it's relevant throughout. So switching back, we're now going to go ahead and just do a couple changes. We're going to, in this capture loop, go ahead and make a tick routine and factor some of the code out there. I'll generate a new method. In that method, I'm going to copy a few things. I'm going to copy whatever I want to have happen per frame. So I want the mapper to happen every single time. So I'm going to go just copy that out. And I'll map from color to depth every single frame. And so depth points will always be up to date. And then I'm also going to go grab the routine to render the color image. Put that there as well. And we'll play mostly inside of this function from now on. I'm also going to call one routine, and that's this.connectImage .update marker data, and it just asks for a few things. The depth points, skeletons, the mapper, the current color width, and the current color format. Okay, we'll quickly go, and that should be the entire step. Let's see how this goes. So now I can click on here. I get these values. You'll notice they're changing now. If I step in front of them, the values are now 700s, 800s, 900s, 1,000, and more. So we now have live feed of exactly how far things are away. And as I spin around, I can tell I'm 6 meters, 8 meters, et cetera. So that's the new ability to get unclamped depth data. So lots of great data there to go build the rest of the talk on, and some great capabilities on top of. So in that method, I went ahead and factored things into a tick method, and I enabled updating markers. And one of the important things there we're doing is we're moving expensive operations out of the data capture loops, out of those using things where I'm copying data out. I'm moving that outside of those usings as well. So next, we'll add skeleton tracking. So skeleton tracking is a key thing. Let's quickly go build the routine. Skeleton tracking is already enabled. I'm going to go ahead and just modify this depth loop here. I'm going to have a skeleton frame. I'll call open skeleton frame on the all frames ready event args. I'll put skeleton frame on my clipboard. I'll no longer check for new formats because we only have one type of skeletons. Sometimes they have 10 joints, sometimes they have 20 joints, but it's the same format. We'll talk about that later. So as long as skeleton frame is null, I want to do some initialization in here. So skeleton frame is I'm sorry, wait, my fault. If the skeleton array is null, I'm going to go ahead and allocate a new skeleton array. So this.skeletons equals new skeleton skeleton frame dot length tells me the array length. That'll be 6 every time, but we still like using constants because we don't like magic numbers. And then we'll go ahead and use the skeleton frame. We'll copy the skeleton data to the skeletons. So that's all I need to do every frame. I now have skeletons piped into my application. And I will go add I'll call a routine, I call mark joints. And let's go look at that mark joints routine. So mark joints routine, here's the declaration. This is in a partial class in another file. This was the skeleton array we had. I'm keeping track of all the people in this frame. There's 6 people at a time, and people come and go. Every skeleton has a tracking ID, so I'm tracking who was there last frame, who's there this frame, so I understand who's coming, who's going. Using this code here, I'm able to see basically who was already there. This person was already there. Is it a new person, or did a person go away? And I handle that differently. So I go ahead and basically talk to my little layer and draw a joint marker on the head, the left hand, and the right hand. If I'm going to go if I have a new person, and I remove those things normally. And then I just collect this stuff. So there's 20 different joint types, the legs, arms, shoulders, head, etc. And let's go ahead and just see this in action, assuming I didn't forget a little step.
When a seventh person enters, are they ignored, or does it bump you?
The question was, if there's a seventh person who enters, does it bump somebody else out? It depends. If the other person's there, it probably stays on him. I'll talk a little bit more about that in a second. So I have a little circle rendering here. I have hands rendering. It may not be able to be seen too well from the back, so it tells me how many meters I am away. Skeleton space is in meters instead of millimeters, so it shows me I'm 1 meter away from the Kinect. I'm the Z space, I'm 1.7 meters away. This number 15 is my skeleton tracking ID. If I go away and come back, it doesn't know it's me anymore. It's going to give me a new tracking ID once it gets me tracked. Hello? There we go. I'm number 23 now. So that's the skeleton tracking ID. So that's just a quick peek at starting to track your skeleton. The next thing I'm going to do is I'm going to talk a little bit about color image formats. Let's just recap what we saw with skeleton tracking. So in the skeleton frame ready or in all frames ready, you get a bunch of skeletons. You copy that into your storage. You can use skeleton tracking ID to understand new people and old people. There's a bonus thing I didn't show you here. Out of those 6 people, there's 2 of them that you can track very closely to understand not just where the center of their body is, but understand where 20 joints are or where 10 joints are, depending on if you're in normal default mode or in seated mode. Seated mode works better in this situation when you don't necessarily have your hips visible in the screen. So I'm getting 10 joints, 30 frames per second feeding into the system, and I'm able to track that and display it, look for gestures, etc. So next, we're going to go ahead and add a little settings module so I can flip between things quickly. And I'm not going to bore you with this code. I'll give you a quick peek. Once I wire this up, it's going to just listen for a key down stroke, and it's going to look for different things like pressing the J key and doing skeleton tracking or not, changing different high-res color mode, infrared mode, etc. And there's handlers for that stuff all in there. In order to wire that into my routine, I'm going to go back to the constructor. I called that class main window settings. I'll create a variable called settings up here. I'll create a new main window settings, and I'll pass in the current window so it knows how to talk to it. And I will also let it bubble down some data binding information to different pieces of my code by setting it to a WPF data binding, a data context. But there we go. Oh, one thing, I ripped out some code. That was a mistake. I didn't need that code. That should be fine. OK, so now I'm going to show you flipping between different color modes. So if I press H, I'm now doing high-res color. It's switching. You'll notice Ben on my team over here says, oh, hey, Rob, high-res color is great. It's got like an ego detection size thing with the circle. I didn't appreciate that. So beyond that, so that's a high res. You get 12 frames per second instead of 30 frames per second, but you get higher res. You get 4 times as many pixels of the color camera. We also have just enabled infrared. So we could turn off the lights in here. In fact, no, just kidding. We could turn off the lights here, and you'd see the same photo, basically, of me. We have an infrared emitter coming out of here, and that's how the depth camera works. And we're exposing this now to developers. And there's a bunch of different scenarios that I'll talk about in a moment that could be used here. Here you see a bit of a dotted pattern because our infrared emitter's kind of spraying some dots around. But we'll talk about that in just a moment. So I'll switch back to color. And one other concept I want to talk about is this looks backwards to you, doesn't it? When I go like this, the arm's backwards. It looks perfect for me. So I've got a little mirror mode here. Does this look better? That looks better. Yeah, lots of nods there. So it's really important when you see something twice, it's very important to have the right perspective on that. So the best applications, if you have to demo a Kinect application, you should have one mirroring here and another mirroring up there. And if you only have one, make it the one that works well for the audience, if you can learn to deal with that. So anyway, so mirroring is important, and my little mirroring component sometimes mirrors the text and sometimes doesn't. I've got a bug somewhere. So mirroring is really important. So we just quickly looked at high-res color format, infrared color format. Infrared color format allows you to see in the dark. Now, importantly, I list here the wavelength that the depth camera is detecting, 827 nanometers. We've also added a feature to be able to force the IR emitter off. So you could turn off this IR emitter and provide a different IR light source if you wanted a cleaner IR image. If you did do that, depth and skeletal wouldn't work at that point, but you'd be able to see more detail. And it's also possible, I've done a little bit of experimentation with this. It's also possible to leave the internal emitter on and provide other IR emitter, like the sun, or well, maybe a different one, and provide better, as long as it's not too intense, you can have a little bit of the best of both worlds, have depth and skeletal tracking working and see pretty well in the dark. So infrared's pretty exciting. Beyond that, we didn't do it just for seeing in the dark, because we could have done that back in 1.0. One of the major reasons we did it is we wanted to enable people to use another device with this camera, with the sensor. We wanted to be able to get a high-res digital SLR camera and to calibrate it with the depth sensor inside of the Kinect. So use a really high-quality, high frame rate color camera and be able to do the mapping that we saw with Coordinate Mapper back and forth between those different things. So there's libraries like OpenCV have some different calibration libraries to be able to do that. Look for samples from us in the future. But the core platform now has that exposed. And once again, mirroring is critical to get right. So let's talk about augmented reality. I'll talk about it first and then code it. You can add objects into the scene. You've already seen some of my simple adding objects into the scene, right? I've overlaid some things. You can base that information on where the skeleton is, so I can put on hats, put on dresses, put on clothes to people. Or based on the environment. Maybe I want to paint objects in the environment and understand where those are. Or annotate things, or put objects there that aren't there on a surface. So what we're going to do now is we're going to write some code to just show. We're going to manipulate the color pixel array to show different distances. And we'll go ahead and do kind of like the NFL does with, hey, the first yard line is here, et cetera. So we're going to go modify that just briefly. So let's take a look to see how we might augment reality. OK, so in order to do this, I'm going to go back down to my tick routine. I've added the settings in here before. I'm going to just quickly go say if this.settings do joint marking, then mark joints. And I'm going to say if this.settings do distance painting. I'm going to paint some distances on the color photo. Then I'm going to go call paint distance, which doesn't exist yet. OK, so I want to be very efficient with walking through all these pixels. So I'm going to use a parallel 4 as my preferred technique to walk through all the pixels and be able to do this on a variety of threads and take advantage of my different cores. So I'm going to loop through all the pixels. And once again, if I want to do that, I need to go from 0 to the width times the height. And whenever that happens, I'm going to pass that variable in as the color pixel index. And this routine that I do in here is going to run and execute on every single pixel. So after I capture it, copy it in here, modify some of the pixels, and then render them with the next line of the code back in tick. So the first thing I'm going to do is I'm going to get the depth image point from the right place using depth points. That's automatically being filled in every frame by the coordinate mapper call earlier. And I'm going to pass in color pixel index. I'm going to go get the right one. I'm going to go get the depth in millimeters is equal to the depth point dot depth. I'm going to figure out, I want to get things around 1 meter, around 2 meters, around 3 meters. So I'm going to go use a div here. Depth remainder equals depth in millimeters. Div 1000. And then I'm going to have a Boolean about, am I near any meter marker? And I'm going to be near a meter marker if depth remainder is less than 150. I'm going to draw 300 millimeter bands or something like that. So depth remainder is less than 150, and depth in millimeter is greater than 0, or depth remainder is greater than 850. So if it's 1850, it'll count and it'll be marked red. If it's 1800, it won't count. It won't be marked in red. It's complaining, I've got one too many parentheses. So I'll say if I'm near any meter marker, I need to calculate a byte index. So I need to, there's actually faster ways to go do this. If I pinned the array, I'll probably do that in a sample in the version I put up here, but this is more understandable. I'm going to go figure out the byte index here is basically the color pixel index times the current color bytes per pixel. So there's typically 4 bytes per pixel for a color, and we've got a color pixel index to the beginning of each one of those things. And now I'm going to go ahead and just manipulate the red, green, and blue directly. So I'll say this dot color pixels byte index equals 0. Copy that 3 times. It's actually backwards. This is blue, green, red. I'll change it to red, 180, and I'll increment the byte indexes. I think this will do it. So let's see how our pixel twiddling is working. Don't fear, I didn't press the D key. And it looks a little strange, I'm wearing red here. But if I turn this, you'll notice we've got 1 yard lines painted. 1 yard lines painted on the walls, on the ceilings, on the people. And we can go ahead and augment reality. Augment reality based on where people are or based on things in the room. Thank you. So it's really important to be really efficient with everything you do with every pixel, because it counts over and over again. Next, I'm going to go add face tracking and show you how face tracking can be used inside of KinectforWindows as well. Now this, I'm not going to write as much code. So I've got a setting to this.settings.do face tracking. If I ask them to do face tracking by pressing the F key, I'll go say track faces. It's just that easy. Now, if I did that, which I did several times during practice, it will just crash. There's one problem that we have with our face tracking engine, is basically we need to copy 2 versions of the depth pixel array. In version 1.0 and 1.5, we kept our depth information in a short, in basically 16 bits. And now we have a better, newer, easier to use thing that you no longer need to go ahead and do bit masking and bit shifting to figure out the player number versus the distance, etc. You could just use that depth. So I've got an array called depth shorts. I'm going to go ahead and allocate a bunch of shorts to store this data. We just haven't updated the face tracking library yet to take advantage of to handle the new format. So we'll do that in the future. So working around that problem now, I'll go ahead and allocate the new depth shorts, and then I will basically copy 2 versions of that depth array. Now this actually points out an important point. In 1.0, 1.5, 1.6, we're backward compatible with each other. We don't have breaking APIs. We might obsolete some APIs over time, but we still provide all of the old functionality. And this is one example of that. We couldn't stop, even though we had a better way of doing things, we couldn't stop doing this. It's not happy with something. It's not depth points. Sorry, I've got a few depth shorts. It compiles, it runs. Let's go see if face tracking is wired up, and then we'll go look at the code. I'll press F. There we go. I'll turn off the joint marking. Might be hard to see in this light. But we have a face mesh drawn onto my face with 87 different positions updating on the fly as it's tracking my face. It understands the rotation, the yaw, the pitch, and you're able to understand where a user is engaged. Is a user engaged with the screen, with the system, with a person, by tracking all of those things. Another great bit of data that we're bringing to you. Let's take a peek at the code. Ignore that. So I just stole some code from Face Tracking Basics in order to do this. We have a face tracker. We're generating some face models. And then I've got a face drawer, bad name, that is rendering those things. If we haven't allocated the face tracker, we'll go ahead and allocate it. We'll also inject the face drawer up into the overlay layer of the Kinect image. We'll clear out the existing face models. We'll loop through. If we're tracking, then we'll go try to call track one face. Track one face passes in the image formats, the color pixels, the depth pixels in the short format, and also passes in the skeleton it's trying to track. So it's got a good idea of where the head is, and it's able to go ahead and spend less CPU searching the whole frame for the face. I'll press Control- and jump back. So then we're able to go walk through. We basically ask for the different triangles that make up the face. We can get the projected 3D shape as well, and then we'll loop through building the face model. And then later on, we'll go render that face model by using some geometry groups in a drawing context in WPF. So face tracking allows you to track one or more faces. It uses color, depth, and skeleton data. It gives you 100 points of your face. It's 87 pixels there and 13 different other areas that we mentioned in the documentation. It tells you the pitch, the roll, the yaw of the head. It exposes something called animation units, which exposes information about your lips, your jaw, your brows. And then also there's different measurements about the width of your eye, et cetera, that we expose through something called shape units. So lots of great information coming in through face tracking. So I want to step back and talk a little bit about what we just saw. We saw that the sensor is providing a lot of great data. It's providing color data, depth data. It's got 2 different sensor streams that we played with in that sample. I didn't touch audio at all. Audio is a great feed. There's a microphone array from across the room. You can, of course, say Xbox play with Xbox. You can do that kind of thing for your application. Give a limited grammar in 6 or so languages that we support right now to allow people to control your application from across the room. It does noise cancellation, and you're able to understand, is it person A or person B? with a little bit of code on your part. Lots of great stuff that feeds into other solutions. We've also exposed in our latest version the ability to get infrared for the in-the-dark seeing reasons, and also for calibration with other computers, with other sensors. And we've just exposed the accelerometer data as well. There's a 3-axis accelerometer in the KinectforWindows sensor, and you're able to go ahead and understand accelerometer data about that. Now, on top of the sensor data streams, there's recognition streams. This is software in the KinectforWindows runtime that is recognizing things based on the color feed, the depth feed, and audio feed. There's skeletal tracking. It's built all on top of depth. You saw that being used today. There's speech recognition. Take a look at speech basics. Take a look at tic-tac-toe samples in the developer toolkit and learn how to dynamically create a grammar or hard code a grammar in an XML file to be able to let a user control your application. We saw face tracking that uses color, depth, and skeletal tracking as well. There's a few application level scenarios as well that are important to understand. Quickly, green screen is a sample in the toolkit where we know where a person is based on their joints. In the depth feed, we also know where every color pixel, whether it's that person or some other person or the background. By knowing the background, you can separate the background, and you can now all of a sudden be in front of Mount Rushmore, have your people inside of Mount Rushmore. Point clouds is another scenario. Take a look at depth 3D and depth with color 3D. There are DirectX examples, Direct 3D examples in the SDK. Because we understand the depth and the color and the spatial arrangement, you're able to go ahead and steer a 3D model and understand live what's happening in this point cloud, in this space. This magic mirror, being able to put augmented reality on top of a color photo, on top of the video feed, is something that you just saw examples of today. And interaction is really critical as well. Jay Kapoor talked about this in yesterday's talk, talked about how to interact with buttons, how to interact with lists of things as well, and some of the advances we're making in those spaces. But I'm really curious, what's next? We've done some pretty cool things with skeletal tracking, with speech, with face tracking. I'd like to bring up Chris White to talk about what's next. He's a program manager on the KinectforWindows team.
Can you switch?
Yeah.
So as Rob said, I'm Chris White. I'm a program manager on KinectforWindows team, and I'm here today to demonstrate a technology we call Kinect Fusion, which is a real-time scanning and 3D reconstruction technology. Oh. First, I need to log in. So as I uncover the sensor, I'll walk you through what we're actually seeing on the screen. So I'll start. I'm going to point the sensor at this table. And in the upper right-hand corner, you saw immediately we got the depth stream live. So that's just what the Kinect is seeing. On the left-hand side, you saw almost immediately we got a real-time 3D reconstruction of the scene. And so this is actually taking the input from the depth camera over dozens and then hundreds and eventually thousands of frames and generating a higher quality reconstruction with information that might not be in any individual depth frame that we see. So as an example right now, you can see the keyboard isn't showing up in the depth frame because it's actually a reflective surface and the IR is bouncing off it. But you see that it's stable in the reconstruction. As I actually move around, you can see that we get more data as we see it from different perspectives, and the model actually gets better. And we can sort of do this across more of the surface as we actually see the screen pop in, so reality populates. So in addition to being able to do this in real time, though, we're able to see changes in real time. So if Rob steps in and moves the hat, we'll see it fade out and then fade back in the new place. So if we do that one more time, this time take a look at the bottom left-hand side of the screen. You'll see that we're seeing this different visualization where, as Rob's hand comes in, it's a different color. So it's new information, something different than what we expected to see based on the reconstruction. So here, So here we're seeing this sort of detailed reconstruction of things on the table, but you can pretty easily scan other things. So if you want to use this to start to map out rooms and understand what's on the walls, you could do that. Likewise, turns out there are other interesting things to scan. So I have one right here. So I can actually see Rob. And if you notice on the 3D reconstruction, you can actually see fine-grained detail like the fact that he's smiling right now, and right down to the individual folds and stuff in his clothing. So the way that we think about this is that it really is an ingredient technology. So there are a lot of different things that you can do with it once you have this capability. So I'm going to switch over for a second. One thing to talk about. So once you have that, you can actually output meshes. You can use those meshes either dynamically in an application, or you can output them and then use them as a digital asset later. So you can pull them into a meshing, into a tool to work with meshes, pull them into video games, stuff like that. So in addition, we're going to show just a couple of simple concept applications of things that you can do once you have this data. So these are not things that this core SDK does, but things that it's easy to do on top of them. So the first one that we're going to see is another augmented reality scenario. So here we're actually able to throw sort of virtual objects and have them now not just paint, but interact with the environment and do physics simulation. Because we have IR, you're also able to do that kind of thing in the dark, which we'll see in just a second. And so now, even though you're not seeing as much of the data coming in on the raw sensor, we still remember where the colors were, and we're still able to show what the room really looks like. So the next thing we're going to see is really cool. It's this idea of, we saw that it was possible to see what was changing. And so in just a second, we're going to see segmentation based on change. So here we're seeing a simple reconstruction like we were seeing here. Notice the teapot. We love teapots in our group. And in just a moment, we're going to see that the teapot's going to move because a person steps in and moves it, just like we saw the hat get moved when Rob stepped in and moved. So the key thing here is when we move, we recognize that something has changed. And instead of just removing it from the scene, we say, that's interesting. There was an intention to move it, and now I know that's a distinct object. And here we're showing object registration, where you identify, this is the thing that you moved before, and now we're doing the digital overlay on top of it.
Cool. Great stuff, Chris. That's really exciting to see Kinect Fusion in action. Now, we've been seeing those videos for a little while, but it's really exciting today to know that it's coming to KinectforWindows. We'll be productizing Kinect Fusion and bringing it to you in the future. So you'll be able to digitize the real world. So now, beyond skeletal tracking, speech, face tracking, Kinect Fusion is going to be another tool that's possible to be used in your applications to build fantastic Windows applications. So to wrap up here, we're driving towards our vision, trying to make sure that computers can see, hear, and understand. We've built over the last year and a half a strong team. We're setting a rapid pace with 3 releases this past year. And we're looking forward to hearing feedback from you to know where you'd like to see us to go in the future. A few things I want to point towards. Andy Wilson gave a pretty inspirational talk yesterday, supernatural interaction. A third to half of those things that he showed there were Kinect-based. Lots of interesting things with multiple Kinects in a room, sensing sound, triangulating on where a person is, and other things like that as well. Jay Kapoor once again did the Kinect UI design considerations. Please go watch those if you weren't able to attend. All week, the KinectforWindows team is going to be downstairs in Building 92. We have a booth. You'll see the big video with depth map and skeleton there. Come ask our team questions. There's a room behind there as well that has a bunch of sensors. So if you want to bring your laptop, you can start coding now and working with us as you install some samples and start modifying them a little bit. We have a website and a blog. Go to KinectforWindows.com. On MSDN, we have lots of great forums. Please interact with us there. And then, of course, on Twitter, we have a team address, KinectWindows. myself, Chris, and Ben Lauer, who's over here as well, our dev community ninja. We'd love to talk with you on Twitter as well. So I'd love to take any questions, and thanks very much for your time this morning. So please do use the microphones. Yes?
Hi, I'm John Callahan from NeoWin. Just a couple of quick questions. First, we've seen KinectforWindows used almost for non-gaming applications, while the Xbox 360 version is used almost exclusively for gaming. When do you think we'll see more PC and Windows 8 games using Kinect? And then I have a question right after that.
Right. So I don't know the roadmap for games. I know that with Kinect for Xbox, we have penetration into millions of computers around. We're not necessarily positioning this to be on every desktop at the moment. We're trying to make sure that verticals like healthcare and education and manufacturing can use it, and retail can use it in great ways. But as it becomes more viable for penetrating into the living room, into the home, into the office, that might become more viable.
Okay. And my other question is, obviously, you guys have been constantly updating the software SDK. Any updates that you can tell us about hardware updates for the Kinect hardware itself?
Yeah, like you say, we're moving fast on software. We're continuing to innovate both there and in hardware space, but we're not talking about specific releases in the future right now.
Okay, thank you.
Thank you. Other questions? Yes.
Yeah, I'm wondering, have you done anything with multiple Kinect sensors in one app, where you've got maybe 2 or 3 giving you much greater detail, definition, and that sort of thing?
Yeah, so we haven't yet built any solutions. I'm sorry, I'm going to actually just live go ahead and see if I can get multiple Kinects running on one machine. I'll run Kinect Explorer. We have some samples, and we totally support that scenario. So if I run Kinect Explorer, I have 2 sensors plugged in right now, as I stole one from the other machine. It's going to go ahead and iterate through those different things. We haven't done anything that makes it easy to go ahead and set 2 sensors up and build one virtual world yet, but we've definitely done a lot of work to make sure all the data comes to you. So here we go. We've got both sensors, and we're getting color, we're getting depth from both of those sensors into one app. We support up to 4 sensors into one application, probably more run than that. You need 1 USB controller per sensor that you have. And it's definitely an area that's interesting to go ahead and figure out how can I have 4 of these in a room and 3 of these in a room and triangulate, et cetera. So there you go. Yes?
Yeah, I'm interested, you mentioned some examples of specifically manufacturing, healthcare, and specifically image to track an object by just seeing it. Is there any demo code, any examples of how I could just see objects and track them and have some intelligent information to report on, that this is this particular object?
Yeah, so we don't have anything built in, and we don't have any samples for object tracking. They're using vision libraries that it's possible to go ahead and do that built on top of a raw data feed. We'd be happy to talk to you in more depth afterwards or in the booth. Okay, thanks.
Hey, Rob, thanks for the presentation.
Sure.
I'm just wondering what kind of data do we get out of the Kinect Fusion once it is available?
Chris, why don't you come up here? I should have had you up here before. Yeah, what is Kinect Fusion going to give the developer?
So the primary output from it is a 3D mesh. Internally, it's building a voxel space representation. So for every little cube of space that it can see, it's saying, is there something there? Is it a surface? What's the angle? But then the way you're normally going to consume that is by creating a mesh out of it through an implementation we have of marching cubes or marching tetrahedrons. You can also do a raycast, so you can create a virtual depth image based on any perspective. So if I basically ask, if I put a Kinect camera here, what would I be seeing? So you can get point cloud data out of it from any particular perspective as well.
So that means that without any 3D development, I can already do, or 3D knowledge, I can already do a lot of stuff out of the box, right?
So out of the box, because it can output the 3D meshes, you can use them in any commercially available 3D modeling application.
Awesome.
And it's trivial to take those meshes and hook them up to DirectX and render them, things like that as well.
And texture on that?
Pardon?
The RGB texture?
So the texturing is something that isn't built in, but is possible to do possible to do on top of. Color is actually super complicated because when you look at things from different perspectives, you actually see very different colors. And so we have some thoughts around what the best ways to do that are, but it's probably not a consistent representation in the volume space. It's probably keeping a series of color images from outside so that you know, as I'm looking from some perspective, I have information from two different perspectives that give me a little bit of data there, and then I'll average the results. So you actually pick up things like specular reflection and matte reflection.
Okay, cool. Thank you.
Thanks. We've got time for one more question, and then we're going to end this. Go ahead.
Yeah, yesterday I asked at the booth, but still not quite sure. So right now, for you to develop the Kinect for Windows, you have one set of hardware, which is not much different from the Kinect for Xbox. Can I use one set of hardware to develop for both platforms?
Yeah, so the SDK does support, for develop purposes, using the Kinect for Windows, Kinect for Xbox sensor. We recommend using the Kinect for Windows sensor. Over time, you'll see that you already see about 4 or 5 features that are unique to the Kinect for Windows sensor. The initial near mode depth was the first thing, but in 1.6 we also did color camera settings and a few other features that are only available with the new sensor. So there are differences between the devices. Kinect for Windows sensor is optimized for Windows, tested for Windows, and some of the chips are different there. Chipsets are different there as well. So, for instance, when we did the color camera settings, it would have been extra engineering work to go do both devices. So, when possible, we release features that work on both because we want developers who have a Kinect for Xbox sensor to still be able to do the vast majority of things. So, for instance, the extended depth data wasn't a difference in the sensor in the depth capabilities. So, we were able to expose that for both. But so we do recommend Kinect for Windows sensors for, of course, every production application, but we do want to support developers with both. Thank you. All right, thanks very much today. We'll be up here afterwards. Come on up to Chris and I to ask more